So hi and welcome to this presentation named Modeling of a Tie Rod Friction Using Neural Networks, Including Quantification of the Prediction Uncertainty. My name is Magnus Malmström, and I'm within this paper together with my supervisors, Isak Skog, Daniel Axel, and Fredrik Gustafsson. And we're all from the Department of Electrical Engineering in Linköping University in Sweden. So I will start with this presentation by motivating why uncertainty prediction is important, especially for neural networks. Then I will move within the title backwards. I will first talk about how to quantify the uncertainty in the predictions, and then apply it to an experimental study where we are modeling the tie rod friction, and then end with some conclusions. So why is it important to quantify the uncertainty prediction of neural networks? So even though neural networks have shown promising results in areas such as computer vision, speech recognitions, they are not as widely used in safety-critical applications, such as autonomous driving. And it's been shown that neural networks are vulnerable to adversarial attacks. If there was a possibility to include the predictions of the neural networks together with predictions from some other model, for example, the model of a LiDAR or detection from the LiDAR, you can be able to do much more robust decisions, which could counteract, for example, these adversarial attacks. But it's not obvious how to integrate neural networks in the sensor fusion framework without the knowledge about the uncertainty in their prediction. Even though we have this problem, neural networks are already used in advanced driving assistance systems, for example, lane keeping assistance and collision avoidance systems. So here's to continue motivating why this is important. So consider the case where we have an autonomous vehicle where neural network is used to estimate the normalized traction force, which is then used to calculate the maximum allowed speed a vehicle can be traveling in. Then we have an obstacle at 5 meters from the vehicle, and then the vehicle is forced to brake to avoid collisions. So in this example, we will see a truck in green that are traveling towards an obstacle, which in this case is a moose that is displayed in brown. And then you will see that we have some estimated friction in red. We have the true friction in blue, and then we have the friction used to calculate the maximum speed here in black. And as you see, the prediction is good, but it's not perfect, or the estimation is good, but not perfect. And this will result in that we think we have too high frictions. So we will collide with obstacles. So we will collide with the moose in this case. But what happens if we include some uncertainty in predictions of the normalized interaction force? And this would lead to that we can take a lower maximum speed, so we'll be more conservative of how much friction we have, so how long it will take us for us to brake. So this is the same scenario, but here we have the dotted line, which is the uncertainty bound of the prediction. And here we use the lower bound of it to make a more conservative guess of how long it takes for us to brake. As you can see, in this case, we are able to stop before the obstacle and hence avoid the collision. So how could this be formulated mathematically? How have we formulated this mathematically to be able to get this uncertainty out of it? So we say that we want to estimate from some noise to measurement S, which you can see here in blue. We want to estimate a parametric model, S hat of M, which depends on parameters, where we find these parameters by minimizing some given cost function. So in this case, it's the square exponent, the mean squared error. And apart from in the prediction, you could see in the red line with dots, but we're also interested, as you've seen, in some variance of this prediction, so variance of this model, so the variance of S hat, which we in this picture can see as the dotted line. So how would we quantify this uncertainty in the prediction? So the main idea is, even though we have a nonlinear model, which neural networks are, if you look closely at the parameters we found, we can consider it to be, we can do local approximations, then it will be a linear model. So then the uncertainty in the prediction will be dependent on how certain we are at our parameters. And how certain we are at the parameters can be seen from the curvature of the cost function at where we're looking on the parameters. So here you can see the parameters, the parameters we have found, and since it's steeper in this direction, we are more certain about the parameters going in that direction compared to the ones that are going in this direction. So how would to formulate this more formally, if you assume that the true systems can be covered by the model set, which is a fundamental assumption we have to do, and given a finite number of noisy measurements of a signal, then the prediction error variance of the model is given by the derivative of the model with respect to its parameters times the covariance of the parameters times the derivative of the model with respect to its parameters transposed. And the covariance of the parameters is given by 1 over the number of measurements times the measurement noise, or the estimated measurement noise, times the Fisher information matrix, the pseudo inverse of the Fisher information matrix, where this Fisher information matrix is given by a rolling mean of the derivative of the model with respect to its parameters transposed times the derivative of the model with respect to its parameters. And the estimated measurement noise is given by the rolling mean of the squared absolute error of the prediction error. So in the literature, two of the main ways to quantify uncertainty is either to calculate the variance and the mean from an ensemble of models or ensemble of neural networks, or include the uncertainty of the predictions as an output of the neural networks. A good thing if you calculate an ensemble is it might lead to more accuracy in your predictions, since you will probably cancel some of the randomness when you take this mean. But it can be very computationally expensive, since already training one neural network is expensive. Therefore, people have come up with clever ways to create these ensembles, for example, using regularization techniques such as Monte Carlo dropout and Monte Carlo batching. If you, on the other hand, include the variance as an output of your model, you have to make some more assumptions on the prediction or the distribution of the prediction. And it also might lead to a more difficult optimization problem. So now we have covered how the linearization method works. Now we want to see it in action. How does this compare to other models, and how does this compare to other ways to quantify the uncertainty in the prediction? As mentioned in the title, the experimental study in this paper is how to estimate the normalized traction force given the slip of a vehicle. And this is a fundamental subproblem in advanced driving assistance systems, and can be used to estimate the minimum braking distance when you're traveling by car. But it might be difficult to measure the normalized traction force, which is given by the friction force divided by the normal force of the car. But the neat thing is that it can be modeled as a function of the wheel slip, where the wheel slip is the difference between how fast the outer part of the wheel is traveling and how fast the vehicle is traveling divided by how fast the vehicle is traveling. So then given some training data, we will train our parametric model, in this case in neural networks, to model this relationship of how the normalized traction force depends on the wheel slip. So the experiment is from a car that's driving on snow with some noise measurement yn, which can be seen here on the plot. Then we will train our model to try to predict the signal. You can see here in red, and it looks quite accurate. It looks like it can sort of predict how the normalized traction force depends on the wheel slip. Then we will quantify the uncertainty prediction using this linearization method. So if we would compare the other methods with this linearization method of how the quantification of the uncertainty looks like, you can see that the linearization method looks quite the same as the ensembling methods, but the network that learn its own uncertainty looks quite different. And this could be a consequence of the highest noise level, so parts of the uncertainty get mixed up in the parameters corresponding to the mean and to the variance of the output. So far, we have assumed that neural networks are a good choice of model to model the normalized interaction force as a function of the wheel slip. But is that the case? So we want to compare to other model structures. So we have compared in this paper to 3 different model structures, both the parametric model given by the magic formula with a bias, and this magic formula is a well-known model for how the normalized interaction force depends on the wheel slip, where these parameters are estimated given some data. And we will add this bias term because the magic tire formula assumes that zero slips is zero normalized interaction force. But since we have some noisy measurements, this might not be the case. Then we'll look at another black box model, which is linear in the parameters, for example, Laplacian polynomials. And then we'll also look at the Gaussian processes with a square exponential kernel, which easily includes the uncertainty in the predictions. And worth mentioning is both the parametric model of the magic tire formula and the black box model that is linear in the parameter Laplacian polynomials. We can use the linearization methods to compute the uncertainty in the prediction. So here we can see the prediction and uncertainty from the magic tire formula, the Gaussian processes, the Laplacian polynomials, and the neural network linearization methods. So all the models give similar model fit, around 70%. And also, if you study the plots, you can see that they capture the prediction error variance quite nice. So they predict how uncertain the different models are, and it looks quite similar for different models. So some final remarks and conclusions. What have we learned from this paper, or what can we learn from this presentation and paper? So we have presented a method how to quantify uncertainty predictions, which does not require either construction of ensembles nor modification of the cost function, which in turn makes that this method could be used out of the box for any network structure that you're currently working on. And the method gave similar results compared to other methods commonly used to predict uncertainty of predictions of neural networks, which indicates that our method seems to be viable. And it's also compared to other models, neural networks gave similar prediction and prediction error variance when trying to model the enormous interaction force as wheel slip. So hence, neural networks could be a good choice of black box models to model these functions. Thank you for listening. And if you have any further questions, either you can ask them now during the Q&A session, or you can email me at this email address.